My name is Chouliaras and I am currently PhD candidate at the University of St. Andrews. I will present to you today a work that has been done during my master's degree at the University of Patra's Department of Physics under the supervision of Konstantinos Gourgouliatos. It's related with the magnetic field evolution on highly magnetized neutron star crust. Magnetic field evolution in the neutron star crust has been theoretically formulating and attributed to the Hall effect and Ohmic decay. The latter is dissipative process while the Hall effect is conservative, making the induction equation rather complex. Therefore, its simulation is more complex and prone to physical and numerical instabilities due to the formation of sharp discontinuities and current seeds that are not formally dissipated unless another dissipate effect takes place. When the induction equation contains only the whole term, application of Euler's seams fails to simulate correctly the propagation of the information within the numerical grid, and this leads to the instability of the seam, as successfully indicated by Fall in 2003. Euler method is the simplest way of numerical integration and straightforward to apply. Realistic neutron star environments being characterized by high conductivity makes it difficult to approach it numerically. Even when sophisticated seams and methods being applied, they reach its maximum nearly 200 Hall parameter, which is similar. The Hall parameter is similar to magnetic Reynolds number. We studied the evolution of the magnetic field in a plane parallel Cartesian geometry using this induction equation. We discretize it using a finite difference seam and then integrate it via the Euler forward method. We focused on the manipulation of the advective terms that appears on the induction equation. We used two different approaches in order to do that. The first is a forward in time and central in space scheme, and the second one is an upwind scheme. We compare them in terms of accuracy and performance. We explore the impact of the upwind method on convergence according to the ratio of planar to vertical field and the Hall parameter. On these tables, you are watching the results of our Hall-MHD simulations using the two different approaches. The C stands for the FTCS scheme, while the U stands for the upwind. Also, you can see which one converges and not. We assess the convergence of the schemes using two different criteria. One physical using the magnetic energy and one based on numerical analysis using the Courant condition. In the limit of a low-strength planar field, the use of an upwind scheme provides a vast improvement leading to the convergence of simulations where the Hall parameter is 2 orders of magnitude higher than that of the FTCS, as you can see on the both tables. Upwind is still better if the planar field is stronger, yet the difference of the maximum value of the Hall parameter is within 10 or a few. Now you are going to watch one of our runs using the upwind scheme in high resolution and high level of the Hall parameter being 2000. The field contours are the vertical field, while the not field ones is the planar field. At this Hall parameter level, the Hall term is dominant, so that's why at the start their behavior is complex due to the interplay between the two fields induced by the nonlinearity of the Hall term in the induction equation. The important thing here is that with the usage of an upwind scheme applied on the advective terms, we are able to see the behavior of the magnetic field evolution on high Hall parameter level. To conclude, our FTCS scheme reaches 100 Hall parameter, which is in agreement with previous work using the same configuration. The most important conclusion is that the use of an upwind scheme on the advective terms greatly improves the convergence of Hall-MHD simulations, and also it enhances the efficiency of the simulations, getting us closer than before to realistic environmental conditions of magnetars. Thank you very much for your time.